So this is a tool that we are going to need for this description of eigenvalues and eigenvectors. So let me just briefly say what they are about before we go ahead and mention what determinants are. If you have a certain matrix, you multiply it by a vector, out comes some other vector. Typically, your input vector x is in some direction, and your output vector y is in some other direction. So you have taken a matrix A, multiplied by x, and out comes y. Sometimes something special happens, that here is your x, and the output is in the extension of x, or exactly opposite to that. Maybe longer, maybe shorter, but is in the same extension as x. If such a thing happens, then that particular vector is called an eigenvector. Eigen means special. And the ratio by which your original vector grew or shrunk, that is in fact the ratio of the length of y to x, that is referred to as the eigenvalue. So eigenvalue is essentially the length of y over the length of x, or magnification factor if you wish. So if y is a certain extension of x, when you take your matrix multiplied by x, out comes something that's perhaps say twice as big as x, or 3 times as big as x, or some other number times x. That other number that comes up, they refer to that as the eigenvalue, and that's what is written as traditional lettering they use for it is lambda. So this lambda gets to be called the eigenvalue, and this x is referred to as eigenvector. Okay, so the main preoccupation of chapter 5 is finding out these special vectors. They turn out to be very useful in a long list of engineering problems. In order to do that, we need some tools. The main tool for that is determinants, and that's why this determinant is showing up at the beginning of chapter 5. Now, as I mentioned, topic of determinant turns out to be rather technical, lengthy. We are just briefly mentioning what we need. So let me just go ahead and introduce determinants a little bit different from what is done in the text by saying some geometrical description of typically not covered that extensively in text. But geometrical, in geometry, you'll measure things like length, area, volume, stuff like that. So if I have a segment of a line, I can go ahead and measure the length of that segment. I could have a shape. Now the shape that turns out to be very useful for us is the shape of a parallelogram. And I might be interested in finding what is the area of this shape. Or I could have something three-dimensional. Imagine a kind of box that has been squished on one side, like this. Suppose you're taking some box, not necessarily in the best shape of it, but perhaps somebody squished it. Sometimes referred to as a parallel pipette. Well, we might be interested in finding the volume of that shape or similar objects in higher dimensions. It turns out that determinants are the ideal tool for describing these concept of these measures that we are interested in. So if I have a matrix that is just made out of a single number, okay, that's going to be a rather trivial looking matrix, then we say the determinant of that is just that number. That could be just the length of a line segments that starts from 0 to A. Now, or A could be on the positive side or could be on the negative side, so this can turn out to be a positive or negative number, but the determinant of a single number is just that number itself. Now, if you look at this parallelogram and you go ahead and look at the sides of it, the sides of it are made out of two vectors. We can go ahead and write down the coordinates of these two vectors either as rows or columns of a 2 by 2 matrix. So I could have something like A, B, C, D, where AB, say, is this green vector and CD is the red vector. Sorry. Okay, so AB is the green vector, CD is the red vector, or AC could be the green one and BD could be the red one. The determinant of this, however we are going to figure it out, turns out to be same as the area of this parallelogram, except that it could be either positive or negative of the area. So this turns out to be either positive or negative of the area of this parallelogram. Same thing in the higher dimensions. If you have this kind of a cube looking thing, you notice that you can make it out of 3 vectors. These are 3 vectors in a 3-dimensional space out of which you can make this box. And you can go ahead, look at one of these vectors, its coordinate or component is going to be perhaps A, B, C. Go look at the other one, perhaps D, E, F. Go look at the third one, say G, H, I. You can write them in rows, or you can take them and write them in columns. Either way, determinant of this 3 by 3 matrix turns out to be either plus or minus of the volume of that shape. So one way of introducing determinants in terms of measure of an object that is made out of a bunch of vectors in a space. You can have a very simple vector here, or 2 of them giving a parallelogram, or 3 of them giving a parallel pipette, and you can go ahead and think about these in that sense. Now, of course, this is just for sake of introduction. We cannot do easy calculation based on it. We are going to go toward the actual definition. Once again, if you have determinant of just one number, if your matrix is made out of one number, like 7, 10, minus 2 or whatever, determinant is going to be just that number. So that doesn't excite anybody all that much. It's just done for the sake of consistency of definition, otherwise doesn't play much of a role. Now, what if I had a 2 by 2 matrix? How do I calculate the determinant of it? Let's write an example, like 3, 4, 5, 7. Many of you might have seen this thing in your algebra classes back in high school or in your calculus classes. So many of you remember how to handle a 2 by 2 case. What do you do in that case? We have certain shortcuts, or a matter of definition. Cross multiply and go according to that. That is 3 times 7 minus 4 times 5. That's going to be 21 minus 20. That is 1. Again, what is the meaning of it? One meaning that you can attach is that if you make a vector 3, 4, 3, the other one is 5, 7. Now they are kind of too, the way I drew it, it's a bit too close to each other. This is 4. Now if I go ahead and make this rather thin parallelogram and try to calculate the area of it. So this was 3, 4, this is 5, 7. If these are the two edges of a parallelogram, I go and complete that parallelogram, the area of it is going to turn out to be 1. Or if I had made 3, 5 and 4, 7, again the area turns out to be 5. So to make it short, if I have this square matrix, its determinant is going to be AD minus BC. Well, what if I had a bigger matrix, say 3 by 3? We go across in two different ways and we get the determinant. Very good. Now these formulas that we are emphasizing and memorizing, these are only good for the sets type of matrices we are looking at. Okay, 2 by 2, 3 by 3. Let me go ahead explain what was just mentioned. I want to emphasize that these are just for memorization, that they do not extend to bigger matrices. So here is an easy way to memorize, but really without much substance to it, meaning the idea cannot be extended to bigger matrices. So let me put a big danger sign here. Before I even mention what we are supposed to do, this does not extend to 4 by 4 or bigger matrices. So it's just the way for us to memorize what's going on here. The idea is to take this matrix and copy it right next to it. At least copy the first two columns. If you want to be nice, you can go ahead and copy the whole thing. Then we are going to make some crossing patterns. That is, consider this line here. Take these numbers and multiply them. If you wish, put a plus sign here indicating we are going to multiply with the plus 1 as well. So let's go ahead and read out what comes out. So I'll have AEI. I'm going to multiply these three numbers, whatever they happen to be. What else am I going to multiply? BFG. And what else? CDH. So I went 3 diagonals in the direction of the so-called main diagonal. Then I go the other way. The other way, you can start from here, or you can start using these depending on your inclination. So AFH, I am multiplying it with the minus. BDI, what's the last one? CEG. Notice that CEG, it was here too. So if you wish, you can go this diagonal and use that and start going backward. You don't need this last column. Or if you want to copy your entire matrix, you have to use one of these two, either the first or last, but of course not both of them. So the determinant turns out to be made out of 6 pieces. Each piece is made of product of 3 numbers. 3 of them are added, and then 3 of them are subtracted. Let's go back, see what happened so far. If I have just one number, I have one term here, just one number. In this case, I have 2, each of them product of 2 numbers, one added, one subtracted. Here we have 6 terms. So see, 1, 2, 6. 1, 2, 6. This is a very famous sequence of numbers. Anybody cares to guess what would be coming next after this? That is, if I had determinant of a 4 by 4. How many things are going to show up on the right-hand side of this guy? Anybody cares to guess? 1, 2, 6. This is a very famous sequence, comes up in calculus quite often. Excellent. It's 24. What is the pattern that you are following? Yeah. This is times 2, times 3, times 4. Every time you up the size by 1 notch, you are multiplying by the new size. This is made out of 24 terms. Each product of, what is your guess? 4 numbers. Like this has AEI in it, that one surely is going to have AFKP in it. 12 will be added. 12 of these products are going to be subtracted. Now, if you try to come up with a mechanism like this to make the answer for this, you are going to see it's not going to work, and this warning sign that I put here is going to be applicable. So that brings us to the issue of, well, how are we going to handle a bigger matrix? This is going to bring us to idea of something that in computer science they refer to it as recursion. Recursion means you have a big problem, you delegate it to something smaller, and they take that smaller problem, delegate it again to something smaller and smaller and smaller until the problem becomes trivial, or just size 1. You handle it from that case and then work your way back up. So we have a If you have a, yes.
I was just getting curious. Okay, you have a determinant like a 4 by 4. Like what you have up there. Could you just take the determinant of A, B, E, F, and then take the second section of D, E, G, H, and go like that, and then subtract the top left minus times the far right minus the lower left minus the upper right? Like breaking down the 4 by 4s? I mean 2 by 2s?
Oh, you mean like this?
Yeah.
And take a determinant of this, determinant of that, determinant of this? No. Okay, this goes through 1, 2, 6, 24. Next one, you multiply it by 5. It's going to be 120. Next one, you multiply by 6, becomes 720. It has a very explosive growth in terms of number of things that's going to be in it. There is truly no easy way of condensing it to any simple formula. It doesn't lend itself to much of anything that's going to be nice, like the stuff you have seen in simple algebra classes. It is truly a monster. And there's one reason we bypassed it is just exactly because of that. It has lots of nice properties that looks magical, given that it is so complicated. There's many, many nice properties that occupied mathematicians for like a whole century. They kept discovering stuff about it. But it is truly complicated, and so it kind of occupies a theoretical place for us, but we cannot dig into it all that much. And there are alternate ways of handling same issues without coming across this kind of a computations. The only reason we are mentioning it is that we use it for handling problems related to eigenvalues and eigen vectors, and we are going to use it for 2 by 2, 3 by 3, at most 4 by 4 matrices. But if there was a bigger matrix involved, we are not going to handle it by using determinants, exactly because of these huge numbers that are involved and the whole thing becoming unstable. So let's go to a so-called recursive definition of determinants. One idea we have is similar to what just mentioned, is reducing the size. Reducing the size means, in this case, if you are given a matrix, you kind of single out a certain member of that matrix, and then you go ahead and eliminate everybody who is on that row and column. So remember, we started with somebody here. If I go ahead and eliminate all the entries that are on that column and on that row, I say I am making a minor of that matrix. If this happened to be, for example, row 3, and that happened to be column 4 of the matrix that we are eliminating, we are going to refer to this new matrix that is made out of the leftover as a 3/4 minor of the original matrix. So if the original matrix is, say, called A, then a 3/4 minor of A refers to taking these guys out and dealing with a matrix that is one size smaller than the one you have. Now, the idea that you were mentioning actually revolves around using these minors, the smaller size matrices, and then takes off from there. Now, if I take this, yes.
So to solve for it, you would want to do one for each row and each column, and make multiple matrices to solve for a total answer, or
Okay.
combine some answer, or what?
Yeah, just
you take out the row and make it smaller.
okay. Let's practice this idea. Let's practice. Suppose I have A, B, C, D, E. Now these are works better for bigger matrices, but I have one example from first you have to focus the way we are going to use it. We focus on a certain row or a certain column. So you have 3 rows to pick from and 3 columns to pick from. You pick one of these things. For example, I might pick this one. Okay. Now what do I do? I'm gonna target each of these elements. First, I'm going to make them minor attached to this C. So I'm going to exclude that column as well as this row. So if I have, let's remember, this is row 1, 2, 3, column 1, 2, 3. So this is row 1, column 3. What's going to be left? Okay, D, E, G, H. That matrix is left, and what we want from that matrix is just its determinant. I could have focused on the matrix, but what we want out of those things are their determinants. Okay, what if I focus on F? So here I picked on C. 1, 3 minor of that is that determinant. The way this idea gets to be used, each element of a certain row or column is going to be picked up, and we are going to do the same thing to them. 2, 3 minor of A is determinant of whatever is left if you kick out this row and that column. Well, who is left? A, B, G, H. And the third list element of the list is the determinant of, in this case, this guy. Once you pick a column or a row, that item shows up in all of these eliminations. So this guy is always eliminated. What is left is what? A, B, D, E. So again, matrix has lots of minors depending on who you focus on. The way you are going to focus is that you are going to focus on everybody on a certain row or a certain column. Which row or column we are going to talk about it later. Sometimes some rows or columns are a lot easier to work with than some others. Okay, so this is the idea of a minor.
And that would give us, and then you would add those together, and that would give you the determinant of the whole thing?
Kind of. We have 2 more steps to identify. So it's a little bit, yeah. We have to take these determinants, multiply by the element that we were focusing. That is, you need to take this. You need this one. Multiply by what? C. Multiply by something else too, which is, okay, there's a third item, which is each matrix comes with a checkerboard pattern of signs. You start with a plus on the upper left corner, and then you flip-flop. So minus, plus, minus, plus, plus, minus, plus, minus, plus. This sign, well, it's easy enough to understand it exactly how it is. If you want a formula for the sign itself, is -1 to the power of row number plus column number. For example, what is the sign for row 1, column 2? Row 1, column 2 would be -1 to power of 1 plus 2. What would you get? -1 to power of 3, which is -1. So that's what the sign is. So the sign is obtained. If you wish, it's easy enough for you to just use this. If you want a formula for it, is -1 to the power of row address plus column address. That automatically creates all of these signs. So what's the sign attached to C? Plus. To F, minus. To I, plus again. Okay. One more definition. It's just a definition. Cofactor is the product of sign, this sign that we have just talked about, times this minor that we talked about. So cofactor, this thing times that, just like to give names, this is a name called cofactor. Like 1,3 cofactor of matrix A is plus times that. 2,3 cofactor, so let's write an example. 2,3 cofactor of A is minus times determinant of A, B, G, H. Okay, now after all this setup, here is a recursive definition of a determinant. Sometimes referred to as expansion definition. Step 1. Pick a row or a column. For each element of that row, determine its cofactor. Multiply each element with its cofactor and add up. So maybe I can, let me see. Did you get that? If we go back up, let's see if we can write everything here. So if this is my matrix A, and I choose the third column to expand on the third column, then I can say determinant of A is equal to, now you help me out to write this out. What should I do? Let's write out everything. Each element multiplied by its cofactor, and cofactor is a minor times a sign. So let's write the plus C determinant of D, E, G, H. What should I write next? Minus. So this guy has a minus. The term itself is a F. Its minor is determinant of whoever is left once you kick that guy out, which is A, B, G, H. What else? Plus I times determinant of A, B, D, E. Now why do they call this recursive? Because once you start with calculating a determinant, then you reduce the problem to a bunch of determinants on the right hand side. But what is it that you gain? These are smaller sizes. Then you have to kind of expand this tree all over again. Like this 2 by 2, again you can go ahead, do by recursion 2, but that's kind of killing a mosquito by an elephant gun. You can just write down determinant of 2 by 2 as DH minus EG, AH minus BG, AE minus BD, or if you want, you can apply this idea all over again and get the determinant. So what you want to do is to practice calculating determinants. This is going to be very important again because you need to do this activity over and over